I asked you to find solutions to that degree 5 polynomial. And so what did we do last time? Well, we said first it's a degree 5 polynomial, there will be 5 roots. Exactly 5 roots as long as you count with multiplicity and you allow for complex roots. We determined how many positive roots there were by using the Descartes' law of signs. So to do that, what do? Well, you count sign changes. 1, 2, 3, 4, 5. Every time the coefficient changes sign. So there will be at most 5 positive roots, and the number of positive roots will be odd. So it could be 5 or 3 or 1. Those are all of the odd numbers that are at most 5. We evaluated p of negative x. It's not written on the board, but it's written up there, I guess. Counted the number of sign changes in the coefficients, found that the coefficients never change sign. So there will be at most 0 negative roots, or just 0 negative roots. We found a list of candidates to be rational roots by using the rational roots test, and there's the list we got. Couldn't be negative, there were no negative roots, so we could throw out the negative options. That leaves us with, I guess, 1, 2, 3, 4, 5, 6, 7, 8, 9 candidates to be roots of this polynomial. And I believe the last thing I asked you to do at the end of last time is between then and today to have determined which of them are actual roots of this polynomial. Anyone actually do that? What do you get? 1 and 3 are the actual roots. I think I agree, but since you're the only one, let's take a moment and do that. So what do you do to check that?
I just plugged in, I started with like 1, the positive 1, and just plugged that into the original equation. See if I got 0.
Awesome. That is exactly what you should do. So, here is what I will ask the remainder to do. There's a lot of computations to do, but there are a lot of people in the room. Not everyone has to do every computation. So I'll split you up by columns. Check whether 1 and 36 are a root. Check whether 2 and 18 are a root. So plug in x equals 2, plug in x equals 18. Use a machine if you like. In fact, you definitely should use a machine, especially to plug in like 18. The numbers will get too varied. 3 and 12. 4 and 9. And I guess that means that I should do 6 myself. So, I'll test x equals 6, and if you're unsure as to what I'm asking you to do, here's what I'm asking you to do. So, I'm going to take the polynomial that I'm studying, and I'm going to plug in x equals 6. So that'll give me 6 raised to the 5th power, minus 7 times 6 raised to the 4th power, plus 19 times 6 to the 3rd power, minus 37 times 6 squared, plus 60 times 6, minus 36. And right, like, if you're a calculator user, that's basically exactly what you'll be computing too. The end result is not 0. So the conclusion that I can make based on this computation is x equals 6 is not a root. And I guess I've already been told that 1 and 3 are roots. As you come up on resolving the calculations I asked you to do, tell me if you find any roots or any non-roots. Maybe I'll just ask this question straight away. Is anyone in this room calculator free today? Not have a calculator at all? Okay, that's good, because the group quiz will basically need some people in the group to have a calculator for this step. Yeah,
3 is a root.
I hear an agreement that 3 is a root. What about the other number you tested? Oh, okay.
I did 12 is not a root.
I hear a 12 is not a root. Does that agree with other people in the column? Excellent. So, 3 is a root. Yeah.
4 and 9 are not a root.
4 and 9 are non-roots.
2 is not.
2 is not a root. What about 18? Cool. So I guess 1 and 46 are the last things on the list. What'd you get? Cool. And that agrees with what you said at the beginning, so great. So x equals 3 and x equals 1 are roots. The rest are not. Cool. That feel pretty good? Nice. So here's the next step. So that finds me 2 of the roots of this polynomial equation. So I guess I can combine that with what I know. There's definitely not just one positive root because I found 2 of them. That means there are either 3 or 5. Let's try to find the rest of them. So there's definitely at least one more positive root. The next step to do is to use the fact that I know I have these 2 roots, so I know I have 2 linear factors of this polynomial. So this polynomial, which I gave it the name p of x at the top to, help, definitely factors as x minus 3 times x minus 1 times Gesundheit times some piece. And remember, the whole polynomial p of x is degree 5. So what do you expect the degree of this thing that's going to go in that blank to be? Degree 3. So, if I can figure out that degree 3 polynomial, I'll at least have made my life better. Instead of trying to solve a degree 5 polynomial, I have to solve a degree 3 polynomial. To figure out those factorization, I guess we have to do some form of polynomial division. So maybe I'll give you the chance for which one should be done. Synthetic division? Polynomial long division. Okay, so now that everyone knows the options, I would like more turnout in the vote this time around. Synthetic division? Polynomial long division. Okay, I actually think the polynomial long divisions have it. And I guess I'll have to do it twice, so I'll do one step using polynomial long and then I'll use synthetic. And as you do this example yourself, do it yourself. So let's use polynomial long division. I'm going to divide the factor that comes from this root in first, just because it's the easier one to deal with. So I want to divide x minus 1 into this polynomial, x to the 5th. And I'm going to be really conscious about space because polynomial long division takes up a fair amount of vertical space. X to the 5th minus 7x to the 4th. If you want to use synthetic division, you'll be done before I am. Plus 19x cubed minus 37x squared plus 60x minus 36. All right, so let's just follow the algorithm that is polynomial long division. Look at the biggest terms. What do you need to multiply x by to get x to the 5th? X to the 4th. So the first term in the result of division will be x to the power 4. Multiply x to the 4 by x minus 1 and subtract the result. So that's minus x to the 5th minus x to the 4th. So plus x to the 4th, leaving me with negative 6x to the 4th. Now you look at that term. What do you need to multiply x by to get negative 6x to the fourth? Negative 6x cubed. So there's the next term in the result of division. Minus 6x cubed. Multiply this by that and subtract the result. So negative 6x cubed, that'll be negative 6x to the fourth, but then you need to subtract it, so it'll be positive. Plus 6x to the fourth minus 6x cubed, leaving me with 13x cubed. This is going to be tight space-wise. All right, so what's the next term in division? What's the next thing you do if you want to finish this algorithm? What's the next step? So you need to ask yourself, what do you need to multiply this biggest term by to get 13x cubed? And what is that? Awesome. So the next term in division is plus 13x squared. So carrying on, minus 13x squared plus 13x squared minus 37x squared plus 13x 24x squared. That's the next term, I think. Minus 37 plus 13 is 24. Minus 24. So the next term in division is minus 24x. And then you just keep on going. Plus 24x squared minus 24x. 60 minus 24 is 36x. So the next term in division is plus 36. And I know that the remainder term should be 0, but I'm going to use that as a checksum to try to detect any errors. Minus 36x plus 36 minus 36 plus 36 is 0. Good, the remainder term is 0. All right, so that was a lot of writing. How many people walked out in synthetic division instead? Did you get an answer consistent with that? Awesome, cool. So let's describe what that step means, and then we'll use synthetic division for the next step. So, what does this mean? So, the original polynomial I'm interested in factors as x minus 1 times the thing on top. X to the fourth minus 6x cubed plus 13x squared minus 24x plus 36. Right, that's just that's what division means. Division is the thing that you need to multiply by to get back to the thing you started with. Okay, so that deals with the x minus 1 factor, but I still expect x minus 3 to be a factor. X minus 3 doesn't divide into x minus 1, so it'll divide into this piece. So I know this piece has an x minus 3 in it. So we need to do polynomial division again, dividing x minus 3 into this term. And I think the two options that I'll give you is I can do that division by synthetic division, or I can be quiet for a little bit while you do the division. Should I do synthetic division? Cool, I'm going to do synthetic division. So I'd like to divide x minus 3 into this piece. So doing synthetic division to do that, 3 for the x minus 3, and now I'll just list those coefficients. 1, negative 6, 13, negative 24, 46. Separated by commas, so I can tell where one number ends and the next one begins. And upshot slash downshot of synthetic division is you have to write way less, but if you don't just remember what the algorithm is, like synthetic division doesn't tell you what to do. You can't figure out what to do if you don't already know. So let's just recall the algorithm. Step one of the algorithm is take this number and just put it up there. Next, take 1, multiply it by 3, and you get 3. Negative 6 plus 3 is negative 3, so I'm going to put a negative 3 up there in the next column. And then just proceed following that plan. Negative 3 times negative 3 is negative 9. 14 minus 9 is 4, so the next term is 4. Four times 3 is 12. Negative 24 plus 12 is negative 12. So I put a negative 12 up there as the next thing. Negative 12 times 3 is negative 36. That's good. My remainder term is 0. That was quick, but did I do synthetic division correctly there? All right. So let's write down the conclusion. That means that this piece, underlined in gold, factors as x minus 3 times x cubed minus 3x squared plus 4x minus 12. So now I have that cubic factor. X cubed minus 3x squared plus 4x minus 12. So, what's the takeaway here? Once you know a bunch of roots of a polynomial, just do synthetic division again and again and again. Pull out a linear factor each time, and you'll reduce the degree of what's left by 1 every time you do it. Feel pretty okay? All right, but we're not in a situation that makes us happy. I managed to reduce the degree 5 problem to a degree 3 problem, but I don't have a formula that solves cubic polynomials. So I don't necessarily know what to do. There is a cubic formula. Did anyone go and look up the cubic formula and go and program it into your calculator or something? Okay, cool. I wasn't expecting anyone to have done that. If you're really excited at a reasonably straightforward example to help you learn the basic language that the calculator uses, it would be a great way to do it. But we don't have that. We have now a degree 3 polynomial that I need to solve. I need to solve this degree 3 polynomial, set it equal to 0. So here's the strategy I'll use. This thing might have some rational roots. It might. In fact, don't use the rational roots test here. What are the only numbers that could possibly be rational roots of this thing? Remember, the original polynomial we found only has 2 rational roots, 3 and 1. So this polynomial could only have 3 and 1 as rational roots. But if this had 12 as a root, then the original polynomial would have 12 as a root, but it didn't. So let's take this polynomial. Let's see if x equals 3 is a root and if x equals 1 is a root. And, well shoot, maybe here's what I'll have you do. I'll have you all do 1 while I check the other. Should I check 3 or check 1? 3? 1. Okay, I'll check 1, you all check 3. That's not what I was expecting. You're having me do the one that's easy while you do the one that's hard. So I'll plug in x equals 1. And I can do this faster by hand than using a computer, so I'm going to do it by hand. 1 minus 3 plus 4 minus 12. Gosh, that's 1, negative 2, plus 2, negative 10. x equals 1 is not a repeat root. Set base. Because I want to see a repeat root. If I don't find a repeat root, then I'm stuck. I don't know what to do next. X equals 3 is? Do I hear a second? Awesome. X equals 3 is a repeat root. Happy. All right, so x equals 3 is a repeated root. So that means x minus 3 goes into this blue piece again. So it looks like I need to do polynomial division one more time. What strategy would you want? Well, either synthetic division or try to like just see the factor by grouping. Can anyone just see how to factor this by grouping? All right, cool. Then I guess you don't need to do the polynomial division. Should I do synthetic division again? Or should I just like wait for someone to tell me how it factors? Should I do? Okay, no hands going up. I will wait until someone tells me how the piece in blue factors. I guess you've already factored by grouping. What'd you get?
X squared plus 4.
I hear an x squared plus 4. Do I hear either agreement or disagreement? I see some agreement. Cool, I see a fair amount of agreement. So I think that means I'm even happy enough that I'm not going to do the synthetic division unless someone says do the synthetic division. Okay, cool. All right, so let's think about what that means. That means instead of solving p of x equals 0, this factorization tells me that I could instead solve x minus 3 times x minus 1 times x minus 3 times x squared plus 4 equals 0. And maybe like instead of listing x minus 3 twice, I should just have a square on it. Does that look like an equation that's easier to solve? Cool, solve it. What are the roots? Well, I guess let's think about why factoring is even the right thing to do. Well, no, you all are walking. You're just going to tell me if I wait, right? Cool, so what are the roots? Yeah.
And x equals 3, x equals 1, and x equals 2i.
Any comments? Anything missing from the list? There is something missing from the list. So chances are when you like got that 2i, you like took a square root and saw a negative under the square root, that gave you the I. But still, whenever you undo a square with a square root, you get a plus or minus sign. And in fact, here's the thing to remember. Whenever you're solving a polynomial equation, if you get one complex root, then the conjugate will also be a root. So there will always be an even number of complex roots. That feel good? Yeah.
Isn't that 4 then, instead of 3?
You upset about this one?
No, 4 total, like,
Yeah. So let's underline this. So there are a total of 5 roots. This only looks like 4 roots.
Oh, because it only happens twice.
That one happens twice.
Okay.
So that's why you need to count with multiplicity. With multiplicity equals 2. And maybe we'll even, like, as long as we're doing that sanity check, finish it up. There are 5 or 3 or 1 positive roots. How many positive roots are there if you count with multiplicity? 3? Because you count this one twice. 1, 2, 3. Yeah. Neato. Does that feel pretty okay? All right. So, here is what I would now like you all to do. I'm going to have you get into the groups that you have arranged. Groups of between 2 and 5 total. I'm going to have you solve a polynomial equation. I might do a bad job counting the number of sheets. So let me know if I fall down.
Esther ESCD.
That's 30. Yeah, I mean, it's hard to separate pieces of paper when they're all. Yeah, I only need 1 copy back from each group. So, and I'm super loose about what you can access and what collaboration rules you are. I know it says no calculator on the piece of paper, but you're allowed a calculator. Ignore that line. That's an error on my part. Use the damn calculator. You need it. I'll also allow access to any machine you want. So if you've got a laptop on you, so you want to use Wolfram Alpha instead when you're plugging in things to a polynomial, use it.
Okay. Yeah.
This is a degree 5. JIAH. Yeah, JIAH. Oh. What is the greatest number of 0 3?
We're not counting.
You saw that.
As I tiny number. Because it's still sign. Then how is it not?
Oh, is that? Yeah. Oh, wait. Yeah.
I copied that number. Oh, never mind.